Ever really thought about the secret life of heat? I mean, it's all around us. Today, we're going to pull back the curtain on calorimetry, the science that explains why a metal spoon gets hot almost instantly in your tea, but the tea itself seems to take forever to cool down. Think about it. You're at the beach, the sun is beating down on everything, right? It's hitting the sand and the water with the exact same amount of energy. So why is one hot enough to make you dance while the other feels so nice and cool? It doesn't seem to make sense. Well, that's the big mystery we're going to solve today, and trust me, the answer is way simpler than you think. So, here's our game plan for cracking this case. First, we gotta get our facts straight about heat, temperature, and energy. Then, we'll uncover the sort of secret identity that every substance has. After that, we'll look at how energy gets traded around, find some hidden heat, and then, the best part, we'll see how this all shows up in your world. Before I leave you with a final challenge.
All right, let's dive in. First things first, to solve any mystery, you have to know the lingo. And in the world of physics, the words heat and temperature are absolutely not the same thing. They're often used that way, but they're totally different, and understanding that difference is our first big clue.
Okay, check this out. It really boils down to this. Heat is energy on the move. It's the flow, the transfer of energy from something hot to something cold. Temperature, on the other hand, is the result of that energy. It's what the thermometer reads. So heat is the cause, and the temperature you measure is the effect. One is the action, the other is the score.
So, we've got our first clue. Now for the real heart of our beach mystery. It turns out that every single substance has its own unique thermal personality. It's like a secret identity that dictates exactly how it's going to react when you apply heat.
And that secret identity is called specific heat capacity. You can just think of it as a substance's thermal stubbornness. Seriously, if something has a high specific heat capacity, it's really stubborn. It needs a ton of energy to get its temperature to go up. If it has a low value, it changes temperature super easily. And of course, there's a formula for it. This little equation is the engine of calorimetry. It says that the amount of heat energy you need, which we call Q, depends on three things: how much stuff you have, or M for mass, its thermal stubbornness, our old friend C, and how much you want to change its temperature, which is delta T. Q equals MC delta T. It's that simple.
And boom, here it is, the solution to our beach mystery. Just look at these numbers. Water's specific heat is a whopping 4,200. Sand is only 840. That means water needs 5 times more energy from the sun than sand does to raise its temperature by just 1 degree. That's its thermal stubbornness in action. The sand heats up fast, while the ocean just soaks up all that energy and stays cool.
Okay, so now we know how things heat up on their own. But what happens when you mix things? You know, like putting a hot rock into a bucket of cold water. This brings us to the most important rule in the game, the great energy exchange. It's such a beautiful and simple law of physics. As long as you've got a closed system, meaning no heat is escaping out into the air, energy is never created or destroyed. It's just transferred. The heat that leaves the hot object is perfectly absorbed by the cold one. It's a perfect trade every single time. And this is the golden rule right here. Heat lost equals heat gained. This simple, powerful idea is what lets us do all sorts of cool calculations, like figuring out the exact final temperature when you mix two things together. But wait, there's a plot twist. Let's say you're boiling a pot of water. You've got a thermometer in there, and you watch it climb all the way up to 100 degrees Celsius. So what do you think happens if you crank the stove up even higher? You'd think the temperature would just keep climbing, right? 101, 102, but it doesn't. It gets stuck right at 100 degrees as the water boils away into steam. So you're pumping all this extra energy in, but the temperature isn't changing. Where is all that energy going? The answer is something called latent heat. The word latent literally means hidden. And that's what this energy is. It's hidden. That extra heat from the stove isn't making the water molecules vibrate faster anymore. It's been given a much bigger job. It's being used to physically break the bonds that hold the water together as a liquid so it can escape and become a gas. This journey from ice to steam shows it all perfectly. You heat up ice, the temperature rises, but then it hits 0 degrees and the temperature flatlines. It completely stops rising while the ice melts. That's latent heat doing its job. Once it's all water, the temp starts climbing again until it hits 100 degrees and boom, another plateau while it boils. 2 changes of state, 2 temperature pauses. So when something is changing state, like ice melting or water boiling, we need a different formula. The temperature isn't changing, so that whole delta T thing is useless. Instead, the heat energy, Q, is just the mass, m, multiplied by L, the specific latent heat for that process. Think of it as the energy ticket price something has to pay to change from a solid to a liquid or a liquid to a gas. Okay, I know this can feel a little theoretical, but this stuff is not just for your exams. These concepts explain dozens of things you see and feel every single day. So let's connect all these dots back to the real world. That thermal stubbornness of water, it's basically a superpower. It lets oceans absorb massive amounts of solar energy without boiling, which is what keeps coastal cities from getting ridiculously hot. It's why a hot water bottle stays warm for hours. It's packed with heat. And it's even why farmers will spray crops with water when a frost is coming. As that water freezes, it releases a bunch of heat, protecting the plants. And that hidden latent heat, it's everywhere. The next time you put ice in a drink, remember this. The real cooling effect isn't just the cold ice touching the liquid. The real magic is the ice absorbing a huge amount of hidden energy from your drink so it can melt. It's literally sucking the heat out. That's also why it feels so cold after a hailstorm. All that melting hail is pulling heat right out of the atmosphere around you. And there you have it. You've cracked the code. You know the difference between heat and temperature. You know about a substance's secret identity, and you know about the hidden heat of changing states. So you've got the knowledge. Now it's time to put it to the test. But before you do, here's a quick look at your new toolkit. These 3 ideas right here are really all you need to solve almost any calorimetry problem you'll come across. This is the stuff to remember. All right, ready for your final challenge? Take a look at these 3 questions. For the first one, think about which tool in your toolkit you need when something is changing state. For number 2, what do you think adding something like salt does to the boiling point of water? And for the last one, remember the golden rule of how heat flows. When you touch ice, which way is that energy traveling? Think it over. Thanks for joining me, and keep questioning the world around you.